Let's go over Internet Protocol addresses and give a little bit of a description about the structure and how they are formed so that we can identify them when we see them in our future work. So at a high level, what an Internet Protocol address is, it's an address that computers can use to find one another on the Internet. It's an address that's written in a way that's particularly amenable for computers to find one another, although it's not particularly memorable or easy for humans to remember these addresses because they're basically made up of numbers. Version 4, IPv4, or Internet Protocol version 4, is the historic standard that describes how Internet Protocol addressing is done. It's widely used across the Internet. It is probably the predominant addressing scheme that's used at the current time, although version 6, or IPv6, is coming very slowly, is transitioning very slowly to take IPv4's place. IP addresses can be used as host names in URLs in many cases. So the motivation for this addressing scheme is that once there are lots of computers connected to the Internet, it's great that they all are able to communicate with each other, but being able to find another computer requires some mechanism of coordination so that one computer, when it's looking for a resource from another computer, can actually have some kind of a lookup number, some sort of phone number, some kind of an identifier, an address, so that that computer can be uniquely identified such that resources can be exchanged with it. As computers connect to the Internet, there are billions and billions of computers that are out there, devices that need IP addresses, and so having a consistent naming mechanism is very important. So computers locating each other. What does that require? How do we do it? IPv4 uses 4 numbers in order to identify the location of a computer. Each number is between 0 and 255, and those numbers are a result of the fact that we're using 1 byte or 8 bits, 8 zeros and ones, in order to specify each one of those 4 numbers. So for example, a particular IP address might have the form of 216.58.219.4. Why do they have different lengths? Why are some 1 digit and some are 2 digits and some are 3 digits? Well, that's because these are being written in decimal form. If we were to convert these to binary form, we would use all 8 bits in order to specify these numbers, so that each one of those numbers would have the same length. So for example, 216 in binary is 11011000. 58 is as specified. That little 2 there is there to indicate that this is a binary number, not a big decimal number just made of ones and zeros. 219 is 11011011, and 4 ends with 100. If we were to look at this IP address in binary, we would see that the different components would be made up of those binary numbers strung together with decimal points in between. They're not treated as decimal points, they're just periods, I suppose, separating the different parts of the addresses. The dominant way that you see an IPv4 address, though, is with decimal numbers, as shown above with 216.58.219. These numbers represent a hierarchy of several different computers or several different networks of computers that are underneath each one of those numbers. They identify a particular computer on the Internet, and so if we think of them as a hierarchy, we could think of the 216 as specifying the root of a tree, the root of one of 256 trees, and below that, another tree, which goes between 0 and 255, or 256 different numbers, a third tree, and a fourth tree. So in total, 4 different trees, each of which can have 256 different branches. That's a lot of computers, a lot of addresses that are available. And so down there at the bottom, at the very base of the address, is a computer, which in this case is slightly off in my diagram, should be coming off of the 4, not the 5. In any event, those 4 numbers specify a particular computer on the Internet, and that number is how you can tell one computer to find another one. Where do these numbers come from? Well, they're actually assigned, batches of numbers are assigned to different organizations by an international organization called the Internet Assigned Numbers Authority, or IANA. They are the ones responsible for making sure that they're equitably distributed among all the different stakeholders that would like to have some of these IP addresses. If you have a particular IP address and you would like to know who has been given it, who has who's been assigned that number, who has the rights to use that number for their computer, you can run a command called whois in a terminal or on a command line in order to look up who's been assigned it. So here's an example of running whois on a terminal in a Macintosh. So I specify the command whois and then the address that I'm interested in looking at. And you can see that you get a bunch of different information about this number, some of it technical. But you can see that in this case, this number is part of a block of numbers going from 216.58.192.0 to 216.58.223.255 that's been assigned to Google. So this is in fact one of Google's addresses for their web search engine. The name information goes on for several paragraphs. You can see their address and different ways of getting in touch with them if you suspect any abuse is going on. If you don't want to do it on the command line, you can also look up numbers going to a website like for example, mxtoolbox.com, which is a good internet website that performs some of these commands for you in a browser, not from the perspective of their server. And the equivalent of running whois on the command line in MX Toolbox is to run the ARIN lookup. The A stands for American, the R stands for regional, I think the IN stands for internet numbers. And so this is a clearinghouse, a database of numbers that have been assigned within an American region. And there are pointers from ones that aren't American to other places in the world. And so here's an example of looking up that same number in the web-based tool, MX Toolbox. So some of the details. Even though there are 256 times 256 times 256 times 256 times 256, or 256 to the fourth, different internet addresses in the IPv4, it actually isn't enough. There are more devices that would like to connect to the internet than there are IP addresses available. And so often one way in which these numbers get shared is that the internet will put smaller domains behind a firewall that can't communicate with each other. These will have a set of local-only addresses that start with, for example, a 10, and then any third number, any second number, any third number, and any fourth number, or 192, 168, any third number, and any fourth number. So if you have a home network and you happen to have seen your IPv4 address of your computer when you're connected to your home address, you'll often find it has an IP address of this form, because what's happened is you've formed a small bit of the internet behind a firewall that other computers can't get to using this address. Local organizations, maybe a university or a workplace, will also often have a small internet behind a firewall that only has these numbers. So as you go from one location to another location, shifting administrative boundaries, you may find that you have similar sets of numbers, but they actually exist in different namespaces that can't communicate to one another. The way this happens is through a technology called network address translation. And what network address translation does is it makes an entire network for an organization, like your home, or your school, or your workplace, look like one address to the rest of the internet. So in this case, what we have is we have the open internet, and we have two firewalls. And the address of the computer that's controlling the firewall on the left is 128.195.4.226. And on the right is 64.136.178.4. So from the perspective of the greater internet, it looks like there are only two computers behind those firewalls. But in fact, behind those firewalls are complete organizations that have their own, that are communicating behind the firewall with each other using internet addresses that start with 10 and have any of the other three numbers as the administrators of that system detail. When you have a firewall like this, connections that start from behind the firewall that go to the rest of the internet are fine. So you can, for example, from your home or from your corporate internet or from your university internet, access a computer like Amazon.com without any trouble. You're starting behind a firewall, going through the firewall, and that creates a place for the remote computer to talk back to you. You've initiated, the remote computer can respond. However, communications that start from outside of your firewall cannot talk to your computer. So Amazon.com cannot reach your computer without you first initiating a connection with it. That's the nature of a firewall. Unfortunately, that means that computers that are located behind firewalls can't connect with each other directly, at least not easily. So if your computer is at home behind a firewall, and another computer is at a university behind a firewall, and you try and connect those two computers to each other, they can't reach each other because they have to go through a firewall that only allows connections to start from within to reach something on the outside. Unless, the only way you can get around this is if someone on the greater internet acts as a connection point for you, a place where you can leave messages so that other computers can drop in and get them and check from time to time. So this, for example, is what Facebook does. Facebook is a location on the greater internet where you can reach from behind your firewall, post messages, share your pictures, read the news, and then someone else can also go to that service on the internet. And in that way, it appears that your computers are connecting with each other, but in fact, they're both connecting with a common computer on the internet. Same way that email works. When you send an email, your email originates behind a firewall, gets passed to a computer in the central internet, and then waits for the recipient to connect to the remote computer that's shared as a common peering point for communications that go between the two computers. There's a special address. There's, in addition to that 10 *** and 192.168 addresses that are reserved for private subdomains behind firewalls, there's also an address that's called 127.0.0.1. It goes by the name of localhost. And whenever you're on a computer, this address, this set of 4 numbers, refers to the very computer from which a connection is originating. And that leads to jokes like this welcome mat that says there's no place like 127.0.0.1, meaning there's no place like home, because that internet address refers to the computer from which a request starts from. So that's IPv4, 4 sets of numbers that identify computers on the internet, but that are not enough numbers for all the computers that want addresses. And so we have firewalls and network address translation in order to make that work. IPv6 uses significantly more numbers. It uses 8 different numbers, and rather than having each number be between 0 and 255, each one of those 8 numbers is between 0 and 4,294,967,297, actually. 298 is how many numbers there are, but it only goes up to 297. Little error on that. Each one of these 8 numbers is 8 bytes. Each one of these 8 numbers is 32 bits. And because they're so long, we often use hexadecimal digits to represent the address. So when you look at an IPv6 address, you'll see something like this one listed above. 2607:F8B0:4007, etc., down to the 2004. That's a complete IPv6 address, and then down at the bottom you can see what an IPv6 address for localhost looks like. It's all zeros with a 0001 at the end. There are certain rules for how you can compress these addresses so that you don't have to list all of the numbers out, especially if there are zeros in the way. And so that address, that's localhost, is often specified just with ::1, meaning that all the zeros beforehand, everything before that 1 is zeros, even though that conceptually there's still 7 batches of zeros, and then 3 leading zeros before the final 1. And as a result, while you can't find welcome mats that say there's no place like ::1, you can find t-shirts that say there's no place like that. So if you're future looking and want a nerdy t-shirt, there's the one to look for. You can use IP addresses directly in URLs. Sometimes runs into various hiccups along the way. But for example, if you type in this IPv4 address, 216.58.2194, then when you hit return, you end up, let me go back a slide. That's actually it. You get Google. So Google is the result of typing in that address. Going forward, you can manually type in an IPv6 address as well. So this is a full address. If you want to do this in a browser, you have to put square brackets around it. And when you hit return, your computer will use the IPv6 protocol to try and find the website address. Now, unfortunately, this requires all of the infrastructure between you and the destination to support IPv6. And in most cases, you'll find that you don't get the result that you'd hoped for because some piece of the system along the way isn't supporting IPv6 yet. Someday it will, and then we'll have lots and lots and lots and lots of addresses available. So in summary, Computers use Internet Protocol addresses to find each other when they're all connected together on the massive Internet. IPv4 is the historic standard and the one that you're most often to see in the near future. And IPv6 is coming along very slowly. Right now we're in a transition stage where many networks are able to use portions of IPv6 alongside a full IPv4 network. Finally, IP addresses can be used as host names in URLs, sometimes in the browser, but in other cases where you need to use a URL as well. Thank you for your attention. Hope this helps explain a little bit more about why IP addresses look the way that they do.